Hi, welcome to the third class in permutation and combination, where we'll study a topic called partition. Before we study partitioning, however, let's quickly revise the concepts we've learned thus far that we will be using. The first one is called the rule of AND. And this says that if activity 1 can be done in m ways, activity 2 can be done in n ways, then the number of ways in which activity 1 and activity 2 can be done is m into n. The next rule is called the rule of OR. And with the same setup, if activity 1 can be done in m ways and activity 2 can be done in n ways, then activity 1 or activity 2, exactly one or the other, can be done in m plus n ways. The next concept we learned was arrangements or permutations. Keep in mind, these are the ones in which the order of objects is important. And we learned that the number of ways in which R out of n objects can be arranged is given by this expression NPR. For calculation purposes, we like to think of NPR as the first R terms in the expansion of n factorial, and mathematically the expression for this is given by n factorial upon n minus R whole factorial. The next thing is selections or combinations. These are cases in which the order of items is not important and the number of ways in which R out of n objects can be selected is given by an expression NCR. C stands for combination. We like to think of NCR as NPR divided by R factorial, and if you were to expand the formula of NPR, you would get that NCR is equal to n factorial upon R factorial into n minus R whole factorial. Now consider that if R in this expression were replaced by n minus R, these two terms would switch around. So we can say that NCR is equal to NC n minus R. This is like saying that if we were to select 2 out of 5 people or we were to reject the other 3, those two expressions would be equivalent. And the last thing we need to revise before we start partitions is repeated arrangements. These are arrangements in which items are repeated. So we said that if there are m objects of one type, n objects of another type, and p objects of yet another type, then the number of unique arrangements you would get with all of these objects is given by, now we know that there are so many objects, so there should be so many arrangements. And to discount the repeated arrangements because say 2 items are the same, we divide by the factorial of each of these. This is the formula for arrangements with repetition. Let us now come to partitioning. Partitioning asks the simple question: in how many ways can n objects be divided into R boxes? Now, depending on whether the objects or the boxes are distinguishable or indistinguishable, we come up with 4 different cases. Let's make those cases. I'll use D for distinguishable and I for indistinguishable. Both objects may be distinguishable. Objects or boxes one at a time may be indistinguishable, or they may both be indistinguishable. We end up with 4 of these cases, and today we'll focus on this case. So here's our case. N indistinguishable objects are to be divided across R distinguishable boxes. Let's take a more concrete example. Let's talk about dividing 5 identical balls into 3 non-identical boxes. Now within this, we end up with 2 cases. Whether or not we allow empty boxes. So those 2 cases would be if we do allow empty boxes and if we don't. Let's start with the simpler case. So here's the case as it stands. We have 5 identical balls. Three distinct boxes, and empty boxes are not allowed. The simplest way of understanding this is a method called stars and bars. And let's use a graphic notation to understand it. We're saying that we have 5 identical balls and we want to divide them into 3 distinct boxes. And when we say that they are distinct, it means that they are identifiable. Let's call them box number 1, 2 and 3. But now on, we'll refer to the leftmost box as box 1. The one after that is box 2 and so on. So the rightmost box for us right now is box number 3. It should still be easy to identify these boxes if I were to remove the first and the last boundary on these boxes. So the space between this wall, this common wall, is box 1. The space between these 2 walls is box 2. And the space beyond the third wall, beyond the second wall, is box 3. Let me just draw it again. It is still easy to identify which one is box 1, which is box 2 and which is box 3. Simply, the one before the first boundary, box 1, between the first and the second is box 2, and beyond the second boundary is box 3. We don't really need the bases either then. All the space before the first wall is box 1, all the space between the first 2 walls is box 2, and all the space beyond the second boundary is box 3. What we have done now is we've replaced 3 distinct boxes with 2 indistinguishable boundaries. These are our bars. What this means is that instead of trying to place the balls in the boxes, we are now going to try and place these boundaries between the balls. That would cause an arrangement of these balls within the boxes, a distribution, right? Given that we are not allowing empty boxes, what are the conditions that we can say? First, where can these bars appear? These bars will now appear in the gaps between the balls, not on the balls themselves, right? So all the valid arrangements, all the valid places for these bars to appear are in the gaps between the balls. We do not allow a bar here or at the end, because that would imply that one of the boxes was empty. If I placed a bar here, box number 1 would become empty. If I placed a bar here, box number 3 would become empty. So these two are not allowed. So now let's ask ourselves something. We started with 5 balls and 3 boxes. The balls were identical, the boxes were distinct. What we have done is we replaced the 5 balls with how many gaps? With 4 gaps. Can I then say that we have replaced n balls with n minus 1 gaps? These are all identical. We have replaced 3 boxes, let's call it R boxes, which were distinct, with R minus 1 partitions, which are now indistinguishable. So if these partitions are indistinguishable, how do we distinguish the boxes? We say that we have 2 identical partitions. It doesn't matter in which order they appear, but once they appear, they cause uniquely identifiable boxes to emerge. The space before the first boundary, no matter which boundary it is box number 1. The space between them is box number 2, and the space beyond them is box number 3. So all it means is now that we need to place partitions within these gaps. However, we still missed one case. We said box number 1 would be empty if a partition had been placed here. Box number 3 would be empty if we placed a partition here. When would box 2 be empty? Box 2 would be empty if 2 partitions were to appear together, because this space between those 2 partitions is box 2. Therefore, we cannot have more than 1 partition in a gap. So our rules have now changed. What we need to do is we need to select some gaps in which these partitions need to come. We have n minus 1 gaps, we have r minus 1 partitions, and since one partition can come in only one gap, exactly one gap, we only need to select r minus 1 gaps out of n minus 1 gaps in which to place one partition each. This problem has now been reduced to selecting those 2 gaps or r minus 1 gaps out of the n minus 1. Can we say that the number of ways of doing this is simply n minus 1 c r minus 1. We have to select r minus 1 gaps out of n minus 1 gaps. If you want to be thorough, then we could use the rule of and say that this is the number of ways in which we can select them, and then we need to multiply with, because we do and, arrange r minus 1 gaps, r minus 1 partitions amongst r minus 1 partitions. That would be r minus 1 factorial, but because these are repeated, divided by r minus 1 factorial, and we can easily cancel this term out. This will always be 1. So this is what it comes down to. If you start with n indistinguishable balls and r distinguishable boxes, then and if empty boxes are not allowed, then the number of ways in which these can be distributed among the boxes is simply n minus 1 c r minus 1. So what's left if we were to allow empty boxes? Let's say that there are n identical balls. R distinct boxes and empty boxes are allowed. What happens? Well, there are 2 ways to approach this problem. Let's look at the most elegant method. Now, instead of looking at these n minus 1 gaps, I'm still going to reduce the r distinct boxes to r minus 1 indistinguishable partitions. Since we can allow empty boxes, I can place a partition here, I can place a partition here, and I can place as many partitions as I want between the balls. Can I then say that this question is equivalent to asking how many possible linear arrangements can I have of n balls and r minus 1 partitions? There is no arrangement that would not be valid right now. I could have all balls first and then all the partitions, or the other extreme, a ball, a partition, a ball, a partition. All possible linear arrangements of these balls and partitions would result in a valid distribution. This is a case of arrangements with repetitions. What are the objects I have? I have n balls and r minus 1 partitions. The total number of objects is n plus r minus 1. So our total arrangements become this upon, and we divide by the factorial of the objects that are repeating. There were n balls and there were r minus 1 partitions. The n balls are identical, therefore we divide by n factorial. The r minus 1 partitions are identical, so we divide by r minus 1 factorial. Now keep in mind that these two terms in the denominator, n and r minus 1, they sum up in the numerator. And this is nothing like but saying that in how many ways can I select n out of n plus r minus 1, or select r minus 1 out of n plus r minus 1. Essentially what that means is that this formula is equivalent to this expression. Obviously this is also equal to and that's the number of ways in which we can divide n identical balls into r distinct boxes while allowing empty boxes.
Now let's look at applications of partitioning. Consider this question. For the equation x plus y plus z is equal to 13, we are asked to find the number of positive integral solutions. It doesn't on the face of it look like a PNC question, but let's ask some fundamental question. What makes one integer different from another? Think of x as an integer as an empty box. What value does this integer hold? It's empty, so its value is 0. What should we add to this box to take it to the next integral value? The next integer is 1, so we need to add 1 to this box. So let's put in a 1. The value of this integer x is now 1. The next integer value is 2, so we need to add another 1. Can we then say that the value of an integer is simply the number of 1s in that integer? Now this is true only for positive integers, but let's hold that for a second. What are positive integers? Positive integers are natural numbers. That is, they are integers starting at 1 and going all the way to positive infinity. So 1, 2, 3, 4, 5 and so on are all positive integers. 0 is not a positive integer. Okay, so we've got that out of the way. Now let's go back to that equation. X plus y plus z is equal to 13. What is a solution for this equation? A solution is basically a set of values for x, y and z that satisfy this equation. For instance, x is equal to 3, y is equal to 4, z is equal to 6 is one possible solution for this equation. Another set solution would be the set 6, 3, 4, implying that x is 6, y is 3 and z is 4. Note that while the numbers 3, 4 and 6 are the same, they have been assigned to different variables, so these two solutions are distinct. We need to find the number of such integral solutions. So in the light of this new knowledge, let's take another look at the original question. Trying to find a positive integral solution to x plus y plus z is equal to 13 can now be thought of as trying to distribute 13 indistinguishable ones into 3 distinct boxes, namely x, y and z, such that no box is empty. So the number of unique positive integral solutions to x plus y plus z is equal to 13 is simply the number of ways we can distribute 13 indistinguishable ones into 3 distinct boxes such that no box is empty, and this looks very much like something we've done. The formula for when empty boxes are not allowed is given as n-1 CR-1, where n is the number of indistinguishable objects to be distributed and r is the number of distinct boxes among which the distribution is to be made. N here is 13 and r is 3. This gives us 13 minus 1 C3 minus 1 or 12 C2 as the number of unique solutions for x plus y plus z is equal to 13, where all values are positive integers. If the question had asked for the number of non-negative integral solutions, then we would simply have allowed empty boxes, because 0 was now a permitted value for x, y or z. Then the relevant formula would have been n plus r minus 1 CR minus 1 to give 15 C2 solutions. But wait, we can solve even the original question using the formula for when empty boxes are allowed. Let's see how. The formula n plus r minus 1 CR minus 1 works in the case where empty boxes are allowed, that is, if we do not need to ensure that something is definitely put into each box. There are 13 ones and 3 boxes. Let's first ensure that none of the boxes are empty. Let's put a 1 in each of the boxes. That leaves us with 10 remaining ones and a 1 each in x, y and z. Now that our condition of not leaving any boxes empty has been met, we can treat the remaining problem as one where empty boxes are allowed. Only now we need to distribute the remaining 10 ones into 3 boxes. We can use the formula n plus r minus 1 CR minus 1, where n is 10 and r is 3. This gives us the number of solutions as 10 plus 3 minus 1 C3 minus 1 or 12 C2. Note that this is the exact same answer as when we use the formula for empty boxes are not allowed.